Hey there everybody. In this toolkit we are going to talk about reasoning with slopes and lengths and how these work in with different geometric shapes. So to start with, lines that are parallel, and we use this symbol of the kind of two slanted lines. Lines that are parallel, if their slopes are the same or if they're equal. So that we know that two lines are parallel if those slopes are the same. That should be fairly straightforward. We know that lines are congruent, and with that we use a symbol with the equal sign with a little squiggle on top. Lines are congruent if their distances or their lengths are the same. Okay? And then last, lines are perpendicular. Perpendicular, we use the symbol of kind of this upside down T, capital T. And we know that they are perpendicular if their slopes are opposite reciprocals. And what that means is if we have something like positive 1 over 4 and negative 4 over 1, those are opposite reciprocals. They've got opposite positive and negative signs, and they are reciprocals of each other. Or we can also say that lines are perpendicular if they're the product, which is multiplication, if the product of their slopes is -1. So let's look at this. So if we say, let's put a little context around this. Let's say if the slope of line AB is 1/4 and the slope of line BC is -4 over 1, then we know that AB is perpendicular to BC because 1/4 times -4 over 1 is equal to -4 over 4, which is -1. So therefore they are perpendicular. So that's kind of two ways that you can do a check. You could check to see that the fractions or the slopes are opposite reciprocals of each other, or you can check by looking at the product of those two slopes. All right, so let's look at some shapes. First we've got this kind of slanted shape where we've got these two sides and these two sides are parallel to each other, so the opposite sides are parallel, and the opposite sides are congruent, and that is a parallelogram. And that's kind of the most general shape that we have. Now, if we take this other shape and we modify it a little bit, modify the parallelogram a little bit, and we say that the opposite sides are parallel, and we also say that all sides are congruent, so all four sides are congruent, then we have a rhombus. If we have this shape here, this looks familiar to everyone, I'm sure, but this shape has opposite sides parallel to each other, opposite sides are congruent to each other, and also all sides are perpendicular, which means they all have right angles. And this, of course, is a rectangle. And finally, if we have this shape here where all of these are the same, so we've got all sides are congruent and we have all sides are perpendicular, then we have a square. Now, the reason I laid this out like this is because we can use the slope and the distance to prove all of these different things by looking at the opposite sides if they're parallel, by looking at their slopes, if they're opposite sides or all sides are congruent by looking at their distance, and we can see if sides are perpendicular to each other using the product of their slopes. So we can prove all four of these different shapes just using distance and slope formulas that we've learned previously. Now we also have some other shapes that you might come across. Oh, sorry, before we get to that, I forgot. I want to talk about the diagonals. With the square and the rectangle, the diagonals are congruent. So if you were to look at the diagonals, those distances would be congruent, whereas the diagonals of a parallelogram and a rhombus are different. So the diagonals in a parallelogram are different from each other, the diagonals in a rhombus are different from each other. Additionally, the diagonals in a rhombus and a square are both perpendicular, and the diagonals of a parallelogram and a rectangle are not perpendicular to each other. So, just some extra pieces that you could also use to prove different shapes using the diagonals as well. So you don't have to just use the sides, you could also use diagonals to help prove different shapes are what they are. But the real goal is to make sure that you are proving it conclusively that that shape is what it is, and that it couldn't be mistaken for another shape because of the points that you've laid out. Okay, so now let's look at some other shapes. So we've got this shape with the top and bottom parallel to each other. So this, we have one pair of parallel sides, and of course this is a trapezoid. We have another shape that looks like this, where we've got the diagonals are right angles. We've got some congruent sides here. So we got two pairs of congruent adjacent sides, meaning the sides that are touching each other, not opposite sides, but adjacent sides. We have diagonals that are perpendicular to each other. And if you have this combination of properties, then you know you have a kite. We have this triangle with all three sides being congruent to each other. And this, of course, is an equilateral triangle. We have this other triangle where these two sides are parallel, or not parallel, I'm sorry, they're congruent. So you've got one pair of congruent sides. And this is an isosceles triangle. And finally, we have this with a right angle and one of the triangles. When we have one pair of perpendicular sides, then of course we have a right triangle. Now, something to keep in mind with some of these triangles is that your isosceles and your right triangle, when you look at these, there might be a special circumstance where it's both, where it's an isosceles right triangle. It can only happen with these two, where those two could be combined. It's not every isosceles, it's not every right triangle, but there is a subset in there where the isosceles triangles could also be right triangles. So this is kind of a summary of the shapes and their properties and how you can use slope and distance formulas to prove that these shapes are what they are. So I hope that helps, and I'll talk to you in the next toolkit.